Hi there, welcome to this Elkchemist Chemistry video looking at condensation polymers. This is going to be a comprehensive study of condensation polymers for both GCSE and A-level, in which we're going to talk about the differences between condensation polymers and addition polymers and some key examples of condensation polymers. And I'll finish by explaining why Kevlar is such a strong material and explaining this diagram here of exactly what Kevlar is doing. If you want to find out, stick around to the end. So with my cup of decaf green tea at the ready, I'd like to start by contrasting addition polymers, a type of polymer we've already covered before, with the condensation polymers we're about to study. So addition polymers are formed by the joining together of many monomers of the same type, multiple times to form a long chain molecule known as a polymer. Now, in the addition polymers we've studied before, this would involve the joining together of many alkene monomers via a free radical addition polymerization process. Now, if you've forgotten about that, hopefully a card should appear linking back to my previous video on addition polymers, which might help to refresh your memory before moving on to condensation polymers in full. Condensation polymers differ from addition polymers in two key ways. The majority of condensation polymers are formed by joining together two different monomers many times over, rather than the same monomer again and again and again. That's not universally true because polylactic acid is a condensation polymer formed from the same monomer, but many condensation polymers are formed by joining together two different monomers many times over. Secondly, the reaction taking place is different. When you join together these different monomers, they will react via the removal of a small molecule such as water or hydrogen chloride, and that's a condensation reaction, hence why these are termed condensation polymers. So the reaction taking place is different to addition polymers as well. Now, I'd like to take you through this general equation for the formation of a condensation polymer known as a polyester. The first monomer you'll see on the left-hand side is known as a dicarboxylic acid, as it has two carboxylic acid functional groups either end of the monomer unit. The red box in the center represents the rest of the molecule, often comprised of multiple CH2 groups in a row. The N that is in front of the monomer is used to represent a large undefined number of monomer units that are present. The second monomer with the green center is known as a diol, as it has two alcohol functional groups at either end of the monomer unit. Again, the green circle in the middle represents the rest or the majority of the molecule, and the N term in front tells us there's a lot of this monomer molecule present. Condensation polymerization reactions often proceed readily at room temperature, joining many of the monomer units together to form a long chain molecule known as a polymer, poly meaning many. To form this particular polyester repeating unit shown, the OH groups from the dicarboxylic acid monomers and the hydrogen atoms from the diol monomers are lost. This will form water molecules. These are the small molecules removed in this condensation reaction, shown here. This will then allow the carbonyl groups, the C double bond O groups on the dicarboxylic acid monomers, to covalently bond directly to the oxygen atoms on the diol monomers adjacent, creating ester linkages as shown and joining the two monomers together. To emphasize this process occurs many times over, the repeating unit shows the two monomers now joined together, minus the OH groups and hydrogen atoms respectively. Empty bonds, as they are known, continue through squared brackets to emphasize the repeating unit continues many times over. And an N now appears after the repeating unit to show this repetition happens many times over to form a long chain polymer molecule. Now you may have noticed that the water molecules removed in this condensation reaction have a 2N in front of them. This is to illustrate that the OH and hydrogen atoms are lost from both ends of the monomers when the repeating unit is formed. So, when N number of repeating units are formed, 2N, or double the amount of water molecules, will be released. Just before I move off of this general equation example, two little things to note. Firstly, some A-level syllabi will use a 2n-1 notation in front of the water rather than 2n. Now this is used to match the number of linkages, such as ester linkages, shown within the repeating unit displayed in the example. Always consult your syllabus to see which your course prefers. I'm going to stick with 2N in my examples because it suits what I'm doing here. And lastly, when you're drawing your own formulae for these condensation polymerization reactions, you wouldn't be blanking out the OH and hydrogens like I'm doing here. I'm doing this to help you visualize how you would form the repeating units shown, but in reality, when you draw these for yourselves, all of these groups would be shown in their entirety, and this would be the layout of an actual equation. Okay? Brilliant, let's move on. Our first worked example is an excellent example of a GCSE level condensation polymerization question. It involves taking lots and lots of ethane dioic acid monomers and joining them together with lots and lots of ethane 1,2-diol monomers. So that's a dicarboxylic acid real example and a diol real example. In the process of this condensation reaction, the OH groups on the ethane dioic acid molecules and the hydrogen atoms on the ethane 1,2-diol monomers will be removed, forming water molecules in the process. This would allow our monomers to join together directly in an alternating pattern to form our repeating unit as shown, with all the key conventions in place, such as the ester linkage holding the monomer units together, square brackets surrounding with the empty bonds going through the square brackets to emphasize continuation of this repeating unit, and the N term being used to emphasize that repetition happens multiple times, and our 2N water molecules being removed because this is a condensation reaction. And that's the end of our first example. A good real-world example of a polyester would be polyethylene terephthalate, or PET for short. This condensation polymer is formed when benzene 1,4-dicarboxylic acid monomers react with ethane 1,2-diol monomers. That would be another example of dicarboxylic acid monomers reacting with diol monomers. Benzene is the delocalized ring cyclic structure shown in the middle of these particular monomers. Now, I won't be expanding upon benzene in this particular video, but I might in other videos on this channel in the future. Plug, plug. Anyway, the OH groups in the dicarboxylic acid monomers and the hydrogen atoms in the diol monomers will be lost as part of this condensation polymerization reaction. The monomers will then join together to form the polymer repeating unit with the key conventions shown as before, and 2N water molecules are also removed as part of this condensation polymerization reaction. PET is used to make lightweight plastic food and drink packaging like this bottle shown here. If you're wondering how I can tell this plastic bottle is made of PET, it's because I'm the Elkchemist, of course. Not really. There is actually a stamp at the base of this bottle with a symbol that looks like this. Okay, and that tells me not only the identity of the plastic, but also will be used for recycling purposes when it's sorted. That's how we can tell what plastics different packaging is made from. Just before we explore another class of condensation polymers, if you found this video useful, please don't forget to give it a like, maybe think about subscribing to the channel, maybe even ring the bell to get notified about latest content. And if you think others would be helped by the content on this channel, please feel free to share that with them so that we can spread the learning of chemistry as widely as possible. As always, your support is hugely appreciated and helps keep me motivated to make videos on a weekly basis. So thanks very much in advance, and let's crack on, shall we? This general equation is different in that it shows a different type of condensation polymer known as a polyamide. Now, these are similar to polyesters we've already seen, except that they utilize monomers that contain terminal amine groups, that's NH2 groups, either side of the particular monomer, instead of the diol used to form the polyesters. If I take you through this general equation, I decided to use a diacyl chloride in place of the dicarboxylic acid of previous examples. It will work in much the same way. The only exception will be that this will result in the small molecule being removed being hydrogen chloride rather than water, because it's the Cls and the hydrogens that will be removed. But other than that, it's identical. So the monomers will react together multiple times. The chlorine atoms on the diacyl chloride will be removed, and the hydrogen atoms on the diamine will also be removed as part of this condensation reaction. The monomers will then be able to join together. A covalent bond will form between the carbon on the carbon double bond oxygen group of the diacyl chloride monomers directly to the nitrogen on the adjacent diamine monomers. This will lead to the joining of the two monomers together via what is known as an amide linkage. That is the carbon double bond oxygen, single bond nitrogen hydrogen group found between these two monomers shown. This amide linkage is structurally identical to the amide linkages that are currently holding all of your protein molecules together in your body as we speak. The repeating unit has the same key conventions as shown in other repeating units we've seen, such as empty bonds going through the square brackets, followed by an N after the square brackets, trying to emphasize the fact that this repeating unit will repeat multiple times over, forming our long chain polymer molecule. Again, 2N is used next to the small molecule removed, in this case HCl, because for every N repeating unit formed, 2N HCl molecules will be removed via this condensation reaction. Acyl chlorides may be chosen to form polymers instead of dicarboxylic acids, as the rate of reaction may be faster or the yields more favourable. But the hydrogen chloride formed as a byproduct of this reaction does bring inherent risk, as the misty fumes are corrosive in nature. So it's very much a process of weighing up the pros and cons here. Our first real-world example of a polyamide is going to be nylon, specifically nylon 6,6. Now, this particular version of nylon 6,6 is being formed from two different sets of monomers. The first monomers are diacyl chloride monomers. These are 6-carbon long diacyl chloride monomers called hexane diol chloride. The hex meaning 6 carbons in length. The second set of monomers I'm going to use are diamine monomers. Again, these are 6-carbon chain molecules, and their names are 1,6-diaminohexane. And you can see the amine groups on either side of the central part of the molecule. You may have noticed as well that I've put CH2 groups in brackets with subscript numbers in the middle of both these molecules. This is kind of a time-saving device. Rather than having to write out 6 CH2 groups in a row in the middle of this molecule, if I write a 6 outside of a bracket and CH2 in the middle, it means that this CH2 portion repeats 6 times. So it's a really neat little trick which saves me time when I'm drawing long chain molecules like these. As we've seen before in condensation polymerization reactions, the chlorine atoms either side of my diol chloride and the hydrogen atoms either side of my diamine will be removed in this reaction. Once these have been lost, the carbon of the carbonyl group on the diacyl chloride monomers will bond directly to the nitrogen on the adjacent diamine monomers, forming our repeating unit as shown, with the amide linkage holding the monomers together with all the key conventions, the square brackets, the empty bonds running through the brackets, and the N emphasizing the repetition of the repeating unit multiple times. And for every N amount of repeating unit formed, 2N hydrogen chloride molecules will be removed in this condensation polymerization reaction. Nylon 6,6 is a truly amazing fibre used in the modern manufacture of clothing and other weave materials. Its tensile strength per diameter is said to exceed that of certain steels, and it was first synthesized by Wallace Carruthers and his team at DuPont in 1935 through serendipitous experimentation. The final polyamide I'd like to talk about is known as Kevlar, famed for its use in ballistic body armors. Kevlar is a polymer formed from monomers of benzene 1,4-dicarboxylic acid reacting with monomers of benzene 1,4-diamine in a condensation polymerization reaction. When this happens, a long chain polymer known as Kevlar is formed with the following repeating unit shown. And as you can see, the OH groups and the hydrogens have been lost in the formation of this amide linkage holding this repeating unit chain together. The condensation reaction itself is identical to those we've seen previously. How does Kevlar stop bullets? It's all down to its chemistry, and it usually is in my experience. Kevlar weave places Kevlar polymer chains in very close proximity to each other. When aligned in this particular way, strong hydrogen bonds, the strongest form of intermolecular force we're aware of, form between lone pairs of electrons on highly electronegative oxygen atoms on one chain and electropositive hydrogen atoms on the adjacent Kevlar polymer chain. This doesn't happen once. This happens a large number of times along the length of these Kevlar polymer chains. These intermolecular forces hold the Kevlar fibers together incredibly strongly in tight, highly regular arrangements. When a high velocity round impacts the Kevlar, it finds it extremely hard to move the fibers apart to continue its forward momentum. And kinetic energy is rapidly depleting as it does so, slowing down the bullet and stopping it penetrating the layers of Kevlar. Kevlar was first synthesized by Stephanie Krolek in 1965, a brilliant American chemist who, much like Carruthers before her, took a chance and spun the fibers she had formed in her lab into a strong, stiff, fibrous material, more resilient than any that had come before. I really hope you've enjoyed this exploration of their chemistry and their uses, and I hope you'll join me for another chemistry lesson very soon. Many thanks for listening all the way to the end, and I'll see you again on the next Elkchemist video. Take care. Bye now.